Okay, let me introduce you very famous, simple, very well-known dynamic example, but really there are not many people understand the dynamics of this problem. Galileo actually understood the dynamics of this problem long time ago. So let's see the problem of pendulum. Frictionless pivot. I have a taut string and I have a mass over here. And I am measuring the angle from here, that is theta. Okay? If somebody's eyes has no dynamics, only static deflection, then I suggest to stand up and go backside to wake up. 한지움? Okay. You can go back. Okay, you can go back and stand up over there. Then you might be able to concentrate on the lecture. You might have some big homework last night. Okay. All right. To apply Newton's second law, what is our first step? Anybody can say, Hanjiu? What is our first step to apply Newton's second law? What we have to do in the first place? Force, we have to find out all the forces, right? Okay, that's very nice. So you didn't sleep. Oh, sorry about that. So, the force acting on this system would be mg due to the presence of gravitational force field. Because I am free the mass that I am going to apply Newton's second law, I have to cut this taut string. That visualize this tension. Okay? And then is equal to Newton's second law says mass times acceleration. Because it is rotating, it's rather convenient to use the coordinate that can well describe the rotational motion. That would be r theta coordinate. So this will be m, and if I write the length of this chord is r instead of l that I used the last lecture, say this is r. R theta double dot. Okay, that is the angular acceleration. What other acceleration is possible in r direction? Everybody forgot? In r direction, r double dot minus, r theta dot square, that is the r direction acceleration. And then the other acceleration in theta direction, there was angular acceleration plus Coriolis acceleration. In this case, r is constant, therefore no Coriolis acceleration is possible, right? And obviously there is another acceleration that is m r theta dot square. The reason why I draw the direction of this acceleration in this direction is because E theta and ER follows right-hand rule. Okay? Of course, you can just say, oh, this is mr zeta dot scale in this direction, but this is more convenient. May I put minus over there? Because it is minus. Right? No? Why not? Why not?
Your direction is not there.
Direction is this direction? Okay. He is correct. Many people were confused. This is the ER direction, and this is the E zeta direction. Which you see, when we have origin over there, the ER direction in this direction and E zeta direction in this direction, R zeta follows the right-hand rule, right? Okay? So if you are convenient to use this, then you can say minus mr zeta dot scale over there. If you want to use this coordinate, you can use mr zeta dot scale. That seems to follow the physics we can anticipate. But in the beginning, as I said, I suggest to you follow strictly the sign convention we learned in the lecture. So please use this instead of that. Okay? So let's erase this. All right. What is the rest of what we have to do? Okay, we just simply write down the equation following the sign convention that we have. All right? So in our direction, I have minus t, and I have minus t equal, minus t, I have the component of mg in this direction as well as that direction, and then this is zeta. Therefore, I have mg cosine zeta that has a plus direction according to the coordinate I'm using, and that has to be equal to m r zeta dot square minus, that's okay. Okay, we follow the sign convention of this. And then zeta coordinate, then I can see no tension contribution, but there is contribution of mg in this direction. That is mg what? Sine zeta. But in this direction, therefore, according to this sign convention, I have to put minus. Okay? That has to be equal to m r zeta double dot. All right? Well, that's good. When I look at these two equations carefully, then I can find that, oh, this is an interesting equation, because that says zeta double dot plus g over r sine zeta equal 0. So if zeta is small, because sine zeta look like that, and this is pi over 2. Okay, and this is 1. Zeta graph, this is a sine zeta graph. What about the graph of theta. Okay, graph of theta will be pi over 2. Pi is 3.1, so that would be 1.5. That is a pi over 2. So I draw theta graph. Then, it is very interesting to note that up to this point, theta and sine theta is very similar. So we can assume that sine theta can be approximated to the theta by observing this kind of physical behavior. Right? Well, this angle is pretty large. So when you see the pendulum oscillating like that, you don't have to solve this complicated equation. You can only solve theta double dot plus g over r, theta equals 0, and you can solve this. This is linear second order differential equation. Okay? If you assume that theta will be harmonically oscillate, then you can say that is a theta 0 sine omega t, assume. Then you find that by plugging this one over there, you get omega square. If you take a derivative twice to the sine, you will get minus, and you got, when derivative of sine would be cosine, and the derivative of cosine is minus, that you got minus omega square and plus g over r is equal to 0. Therefore, you got omega square is equal to g over r. And omega, as you know, is 2 pi f. Therefore, you have f square is equal to 2 pi f square equal to g over r, 1 over 4 pi. Therefore, the frequency is equal to 1 over 2 pi square root g over L, and the frequency is 1 over period, so you can estimate the period, and then you can, sorry, this is R. So you can see immediately that the frequency of a pendulum will increase as I decrease the pendulum length R, right? So maybe I demonstrate using this because I didn't bring any. I forgot to bring my. Let me use your mass over here. Right? Okay. It's a good pendulum. Okay. You will see the period, right? But small one reduced, not linearly, but in terms of square root, right? Okay. Maybe I increase more. Hoping. Pretty slow. Reduce. Faster, right? So according to the result we have.